Assalamualaikum and hi. Today our group will be presenting about finding the best fit equation to represent our data, which is in unemployment rate in Malaysia.
Today, we can analyze Malaysia's labour market from 2018 to 2025. Let's examine Malaysia's recent economic landscape. The data shows a U-shaped recovery curve post-COVID-19, with unemployment peaking at 4.9% in 2021 before stabilizing to 3.8% by 2025. To better understand these trends, our project aims to go beyond observation. We are using Maple to perform regression analysis on this dataset. Our primary objective is to find the best fit line using three distinct mathematical models, which is linear, quadratic, and cubic. By comparing these models, we can determine which best captures the complexity of the economic shift from pre-pandemic levels to our current new normal. This quantitative approach helps us move from simply describing the data to accurately modeling the trajectory of the Malaysian labour market. Then, we continue with linear model.
So next, to the linear curve. So first, I constructed matrix A and vector B from the given data. Next, I formed the augmented matrix M equal to A augmented with B and applied the RREF to check whether the system has an exact solution. Based on the Maple output, the system is inconsistent, meaning it has no exact solution. So next, I calculated the transpose of matrix A denoted by A transpose. Then I computed A transpose times A, written as A transpose A, and A transpose times B, written as A transpose B. Then after that, I calculated the determinant of A transpose A. The determinant is not equal to 0. This means A transpose A is invertible, so the normal equation has a unique solution. To solve the normal equation in Maple, I obtained the following coefficient. A equals to negative 80.3417 and B equals to 0.0417. Therefore, the final linear regression equation is next. The Maple generated a graph that shows both the original data points and the fitted regression linear. The scatter plot represents the actual data, while the curve represents the regression model. From the graph, we can see how well the regression equation fits the given data and captures the overall trend. Finally, to calculate the error vector using the formula, error equals to b minus a times x. Then I calculated the Euclidean norm of the error vector. The value obtained is approximately 1.246. This value represents the overall difference between the actual data and the values predicted by the regression model. So next, to the quadratic equation. So once again, we do the same exact solution to find the RREF to check whether the system has an exact solution. So once again, we computed the A transpose A and A transpose B, and we calculated the determinant, and it same as just now, the determinant is not equal to 0. So that means the normal equation has a unique solution. So by solving the normal equation in Maple, I obtained once again with the following coefficient. A equals to 265,196.38 and B equals to 262.34 and C equals to negative 0.0649. And therefore, the final equation is next. We once again generated a graph shows the whole data, and finally we calculated the error once again, calculating the Euclidean norm of the error vector, and the value obtained is approximately 268.5125615, and this value represents the overall difference between the actual data and all the value that we calculated just now.
Okay, next I will explain about the cubic curve. For this curve, first we form the augmented matrix from matrix A and vector B, and then we applied the reduced row echelon form RREF. Based on the Maple output, the system is inconsistent, so we need to apply the least square method For this method, first we calculate the transpose of matrix A denoted as AT, and then we compute A transpose times A written as ATA, and then A transpose times B written as ATB. And then we calculate the determinant of ATA, which we got not equal to 0. So it means that ATA is invertible and the normal equation has a unique solution. So we solve the normal equation, which is ATA ATB, and then we obtain the following coefficient, and we got this equation. For the graph, we generate both the original data points and the fit regression curve. The scatter plots represent the actual data, and the curve represent the regression model. So finally, we evaluate the accuracy of the model by calculate the error vector using the formula B minus EX. And this value represents the overall difference between the actual data and the value predicted by the regression model.
After comparing error values from all models, we found that the linear model was the most suitable for our data since it has the smallest error value. This is because it provides predictions that are the closest to actual data if the model has the smallest error value. To obtain the predicted unemployment rates, we substitute the years 2015, 2016, and 2017 into the linear equation model. The predicted unemployment rates are 3.6838% in 2015, 3.7255% in 2016, and 3.7672% in 2017. The predictions show a gradual increase in unemployment rates over the years. This suggests that if the trend continues to rise slightly, therefore, the linear model provides a useful estimate for future planning and analysis.